Hello and welcome, everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will discuss PFAS contamination in Minnesota, with a focus on lessons learned, fate and transport, and reducing exposure. With that, I'd like to introduce our presenters for today. We're pleased to have with us Ginny Yingling, Senior Hydrogeologist in the Environmental Health Division of the Minnesota Department of Health. Ginny Yingling has been the agency's lead investigator of PFAS since 2003, and she has over 25 years of experience working on contaminated sites. She's also the co-chair of the Interstate Technology and Regulatory Council's PFAS team, a group of over 390 environmental professionals drawn from state and federal agencies, academia, industry, consulting, and public interest groups, which has developed a series of fact sheets on PFAS, conducts PFAS training events, is developing a PFAS risk communication toolbox, and is preparing a detailed report on the current state of knowledge regarding PFAS. We're also pleased to have with us today Dr. Kristen Thoreson, Research and Development Director at REGENESIS. Dr. Thoreson is the lead inventor of Plume Stop liquid activated carbon. She heads the chemical research and product development program at REGENESIS. Her team is focused on developing advanced technologies for the treatment of recalcitrant compounds in mixed environmental media. She graduated with a doctorate in chemistry from the University of Minnesota, and both her graduate and postdoctorate research focused on mechanistic investigations of chlorinated ethene degradation pathways using molecular models and compound-specific isotope analysis. All right, that concludes our introduction. So now I'll hand things over to Ginny Yingling to get us started.
All right, well, thanks, Dane, and thanks everybody for tuning in. As many of you know, Minnesota made an early entry into the PFAS party, in part because of a major manufacturer located just southeast of St. Paul along the Mississippi River, where PFAS has been manufactured at a chemical plant since the late 1940s. And waste disposal at the plant occurred at 3 major offsite facilities in nearby suburban communities, as well as in burial pits on the manufacturing plant property itself, and for a very brief period at a small dump site near downtown St. Paul, although the majority of the contamination from that site now is being largely attributed to wastewater treatment plant sludges that were disposed of there over the last few decades. In 2004, PFOS and PFOA was detected in the city water supply wells in the city of Oakdale. And subsequent investigations have led to identification of a plume that covers over 150 square miles of contaminated groundwater as well as surface water. The map that you're seeing here on this slide is of perfluorobutanoic acid, PFBA. It's the most soluble and mobile of the PFAS that we detect associated with these sites, and so it's the most widespread. But as you can see, it's covered a large area, essentially the southern half of Washington County, which is located just to the east of the Twin Cities metropolitan area. The contaminations affected 4 major aquifers and the drinking water supply of 13 communities, including 8 municipal systems that serve over 140,000 people. We've also identified contamination in over 2,700 private wells and have issued drinking water advisories in more than 1,100 of those wells. So we've had a long period of time and a lot of sampling points to work out some of the fate and transport of these chemicals, and have learned some interesting lessons along the way that I'd like to share. One of the things that's been driving this investigation, though, are the low and ever evolving drinking water standards. And as you probably know, Minnesota and several other states have recently set quite low drinking water guidance values. And so I wanted to touch on that very briefly first, and then that'll help put into context the evolution of our site investigations. In recent years, as many of you probably know, research has indicated that longer chain perfluoroalkyl acids, or PFAS, are highly bioaccumulative, so that part per trillion in the drinking water can lead to parts per billion in blood serum, and that ongoing exposures can lead to a lifetime steady state concentration in the blood serum. As a result, there's detections of PFAS in the blood supply of pretty much everyone in the developed world, including the United States. The thing that is driving the low drinking water values in states like Minnesota and others is that when we look at both the intake rates, especially for infants, where we see very much higher intake rates for infants, and the biological activity of these chemicals at very low exposure levels, this has led to a concern about significant potential for exposure for babies who are born to moms who have been exposed for a long period of time, both due to placental transfer. For example, PFOA, it crosses the placenta at a concentration somewhere around 60 to 200% of the concentrations that are found in the drinking water that the mother's consuming, but also through the breast milk. And at that point, it's more reflective of the mother's serum concentration, but those are in parts per billion because of the bioaccumulative nature of these chemicals when they're in our drinking water. So based on that, Minnesota has set a series of drinking water guidance values starting in 2002, when we were first approached to evaluate PFOA and PFOS for health risk limits. And so at that time, we set some guidance values at fairly high levels of 7 and 1 part per billion for PFOA and PFOS. You can see from this table how as more science has, or as the science around these chemicals has evolved, our allowable concentrations in groundwater and drinking water has decreased over time, so that currently we just released new values earlier this year for PFOS at 15 parts per trillion, and finally set a number specifically for PFHXS of 47 parts per trillion. We've also got low values for PFOA, and then slightly higher levels allowed for PFBA and PFBS, because those two compounds don't appear to bioaccumulate to the same degree that the other chemicals do. It's been this ever evolving understanding of the toxicology of these chemicals and their detection in the groundwater in the East Metro that's led us on our investigations and driven our findings out there. I'll return to this map, and what it helps to illustrate is that because perfluoroalkyl acids are highly soluble, and some of them tend to be very mobile, all of them are extremely persistent, they can generate very large plumes, and in fact, early modeling of the groundwater in this area emerging from the two northern disposal sites suggested that we should have very small plumes, which are shown by the black hash marking on these maps. This is what was predicted based on particle tracking of water that would be leaving those two disposal areas, and was done to try and determine which of the disposal areas was actually affecting which of the Oakdale City wells. But as you can see, the area affected by the disposal sites is much larger than anything predicted by basic groundwater modeling. In part, that's due to the fact that we have commingling of these plumes, but also because the contaminants are so soluble and so mobile, they're acting as groundwater tracers. And so we get much larger areas of contamination than we would generally expect to see. And some of that we had hoped would be constrained by the fact that we have a large groundwater divide in this part of the county. The county is bounded to the west and to the south by the Mississippi River, which of course is a major drainage feature and a major groundwater discharge feature. The county is also bounded to the east by the St. Croix River, which is a major tributary to the Mississippi. So there's a groundwater divide that essentially bisects the county north-south, and groundwater on the west side of that divide typically flows west-south or south-southwest towards the Mississippi River. And you can see the major areas of contamination. I got ahead of me a little bit. The major areas of higher concentration contaminants are on the west side of the divide. So our early investigations, which focused near those source areas, seem to be consistent with what we expected in terms of the groundwater divide, keeping the contamination on the west half of the county. It wasn't until later, when we had a longer target analyte list and more sensitive analytical methods, that we started finding this large, low concentration plume of PFBA, and realized that it was actually on both sides of the groundwater divide. One of the other major things, because of the groundwater or these contaminants acting as tracers, is bedrock features are controlling contaminant migration to a degree that we typically don't see at some of our other sites. So in this area, we have some fairly significant incised bedrock valleys that were formed as the glaciers retreated. These are old tributaries to the Mississippi and to the St. Croix. They show up on the map here as the dark features underlying the plume. And although they've been backfilled by the retreat of the glaciers and filled in with sediments shed off the glaciers, they still act as tributaries in some cases, and in other areas where they filled with fine-grained sediments, they act as barriers to groundwater flow, and so they affect where we find contaminants. But as you can see down in the southern portion of the map, the PFBA concentrations even map out the bifurcated bedrock valley that underlies the southern disposal area. We also have a series of major bedrock faults in the southeastern portion of the site. There you are. And those also appear to be controlling some of the distribution of the perfluorinated chemicals, especially this little weird fault block area. We find each little fault block has a different concentration and distribution of the chemicals. But one of the things that we weren't prepared to find, and that I want to focus in a little bit about in terms of fate and transport, is the important role that groundwater and surface water interactions have played. And it provides a cautionary tale for all of our sites where there's any runoff from the site to a nearby surface water. It means that our investigations need to be particularly attuned to where that surface water might be going and where it may be infiltrating back to groundwater, and the potential risk for isolated plumes being developed by that groundwater surface water interaction. We also see some interesting partitioning of the PFAS chemicals because of their different solubility and absorption profiles. And so we'll also see a quick case study of that at a small part of this site. So to illustrate the surface water groundwater interaction, I'm going to walk you through a little bit of the evolution of our investigations of the two northern disposal sites. So we're looking at a close-up of the disposal site in Oakdale, Minnesota. This was one of the earlier disposal sites, and then over time, disposal ended at this site and shifted over to the Washington County landfill, which was the state's first permitted landfill, but it was still an unlined landfill, and so in direct communication with the groundwater. And when we look at the PFOA concentrations emerging from both of those sites, we see a fairly normal looking plumes, and pretty much exactly where the modeling would have predicted that we would see these plumes, and even the extent looks about correct. But as our analytical methods evolved, we began to detect PFBA, we stepped out further beyond the areas where we had detected PFOA initially. We thought we'd defined the down gradient extent. We were finding clean wells in this area. But with the detection of PFBA in all of those wells, we expanded the scope of our sampling area and started finding hotspots of PFOA further down gradient. We thought, well, perhaps that's still associated with this plume, and maybe we're just missing the hydraulic connections. There's a large regional park where we have no monitoring points, and so we figured, well, maybe that's just groundwater flow that we haven't completely defined. We could also see some excursions of the PFOA across the groundwater divide, but there's a small buried bedrock valley where this little finger of PFOA is located, and so we assumed that it was just traveling along that. But as our investigations continued, so here's the groundwater divide. As our investigations continued, we were seeing PFOA in private wells on the east side of the groundwater divide. And so we started to have some questions about why that would be. And as our drinking water guidance values were reduced over time, starting in about 2015, we did more sampling to the east and ultimately have detected an area of contamination off into some townships towards the St. Croix River that are pretty hard to explain based on our understanding of the groundwater transport in this area. What helped us to understand what was occurring, I'm going to skip past that, is when we also looked at PFOS. I mentioned that the disposal of PFAS occurred first at the Oakdale disposal site. By the time disposal was occurring at the Washington County landfill, the chemistry that was being used at the manufacturing facility had shifted from a fairly equal mix of sulfonates and carboxylates. And at the time of the disposal at the Washington County landfill, it's dominated almost entirely by the carboxylates, so PFOA, PFBA, PFPEA, and PFHXA. We find very little PFOS in the landfill. The highest concentration was 1 part per billion. And by the time we get just a short distance down gradient of the landfill, we have several hundred wells with no detection at all of PFOS. And yet a little bit further south of the landfill, and we were finding concentrations in private wells up to 3 times what we were seeing in the landfill itself. And it wasn't until we mapped out PFOS by itself that we realized that all of the PFOS detections in this hotspot were south and west of a stream, which headwaters in the wetlands where the 3M Oakdale disposal site is located. So in that area, we've got wetlands that are discharging to the stream, and by the time the stream reaches the city of Lake Elmo, it becomes a losing stream and infiltrates to the groundwater. So that began to help us understand what was going on with the contamination, that we actually were having surface water emerging from the disposal site in Oakdale, traveling to the east into Lake Elmo, and then re-infiltrating and creating an isolated plume down gradient by about a mile from the source area. As our investigations continued, though, we realized that we had a much larger issue on hand as we were finding the contamination out into the township. And at about the same time, we were made aware of a stormwater interconnect project that appeared to be associated with that. This map shows that project as a series of pipelines and ditches that interconnect from the city of Lake Elmo and out into the townships. The purpose of that was to control flooding on these 3 northern lakes and also to protect this lake here. This is Lake Elmo itself. It's a high resource recreational lake and fishing lake. We were trying to protect it from stormwater influence and degraded water quality flowing from this lake in a large regional park, Eagle Point Lake. And so the watershed district interconnected the outflow from these 3 lakes, lowered the lake levels and tried to maintain them, and then put all of that water into a stormwater system that entered Raleigh Creek. So the same creek that was carrying the PFAS from the Oakdale disposal site. For a short period of time, there was a groundwater pump out system operating at the Washington County landfill that also discharged to that stormwater system. The thinking behind that was, at the time, all that was known in the Washington County landfill was industrial solvents that were degradable if they could be exposed to oxygen, sunlight, and bacteria. And so water being extracted from that site as a gradient control mechanism was discharged for a period of 7 years to that stormwater system. So all of it ended up eventually entering into Eagle Point Lake. From there, the water from Eagle Point Lake flows through a creek and then enters a pipeline that's actually run across the bottom of Lake Elmo into a series of ditches, ponds, and culverts until it ends up in another lake called Horseshoe Lake. And from there, it re-enters a series of ditches and stormwater ponds, and then finally is put into a pipeline, a stormwater sewer that runs along Interstate I-94 and eventually discharges to the St. Croix River. So we sampled the surface water system, both that interconnected stormwater system as well as nearby tributary sources. And when we map out the PFOS, we can see that there's a clear gradient of high concentrations near the Oakdale source area, and then decreasing concentrations as it moves through the system. But by the time it gets out into the townships, the concentrations remain pretty much constant as they head out to the St. Croix River. And all of these exceed our drinking water guidance values. Anything that shows above the purple, well, the blue coloration now exceeds our drinking water guidance values. But we found little or no PFOS in any of the nearby surface waters that are tributary to that system. So it's pretty clear evidence that the Oakdale disposal site is the primary source of PFOS in this system. And when we map the groundwater plume over that surface water sampling data, you can see a very close correlation between the results of both the surface water and the groundwater. So the pathway that we've identified for how these plumes developed is both a groundwater and a surface water system. So the groundwater shown in the light blue arrows, the surface water is shown in dark blue, and it starts with the formation of the groundwater plumes at both sites just through infiltration from the disposal areas, but also groundwater discharging to the surface water, Raleigh Creek, and then flowing east into Lake Elmo, where it becomes the losing stream that I mentioned before, enters the groundwater and then follows regional groundwater flow to the southwest. And the concentrations that we find in the surface water there is almost identical to what we found in the private wells that are about 150 to 200 feet deep. So it gives you an indication of the conservative nature of these chemicals once they're released in the environment. There was also the surface water contribution from the pump out system for 7 years from the Washington County landfill. All of that flowed with the creek into Eagle Point Lake, which is largely a closed basin lake. So much of that re-infiltrated to the groundwater, picked up with the regional groundwater flow and heads off to the southwest and impacted hundreds of private wells down gradient of those features. There is also a minor groundwater connection between Eagle Point Lake and Lake Elmo. So we did see some flow through shallow groundwater wells in the park. We pick up the similar concentrations in the lake itself and in private wells on the down gradient edge of the lake. So now we're on the east side of the lake and on the east side of the groundwater divide. There's also that surface water connection that goes into the pipeline. It enters Horseshoe Lake where it again re-infiltrates and hits the groundwater, but there's also the surface water connection through a series of stormwater ponds and then into that pipeline that goes to the St. Croix River. All along that pathway, we've got groundwater infiltration from the stormwater ponds. It's also entered a buried bedrock valley, and from there it all flows east out to the St. Croix River where it discharges. So the point of all of this is to illustrate the fact that if we don't do a good job of sussing out the surface water and groundwater interactions, we could be easily fooled by the appearance of discrete plumes throughout our system. For example, this area in West Lakeland Township that emerges from the Horseshoe Lake infiltration is 6 miles from the source area for the PFOS. And so it's a cautionary tale to be very careful about evaluating both surface water and groundwater to understand your plume migration. I'm going to skip along to show a small area that was impacted by AFFF. It's superimposed over our plume in the southern part of Washington County. There was a major chemical fire that was put out with multiple types of AFFF from 3 fire departments that responded to the fire. And the contaminant, or the foam, ran off from the site to a drainage ditch and into a stormwater pond where it's infiltrated to the groundwater. This fire occurred in 2003. We were picking up contamination in nearby private wells that reflected the same chemical signature that we see in the surface water. We were picking that up in 2007 and the concentrations are still increasing. So it gives you an indication of how quickly these chemicals can migrate and infiltrate down to wells that are up to 250 feet deep nearby. But you can see, and the signature in the soil is dominated by the sulfonates, PFHXS and PFOS. There's also PFOA and PFBA are primary constituents, but at much lower concentrations. But when we look at the sediments, similarly, PFHXS and PFOS still dominate, but the relative concentration or relative abundance of PFBA and PFOA has increased relative to PFHXS and PFOS as the sulfonates are starting to partition out and the carboxylates are migrating further down the system. And when we look at the surface water, we find that PFBA and PFOA are now the dominant constituents, whereas PFHXS and PFOS have nearly dropped off from the signature. And this signature of it found in the surface water is nearly identical to what we're finding in nearby private wells. As many of you have probably heard, there was a major settlement between the state and 3M, the manufacturer, and so we've been working through a public process that's being led by our state pollution control agency and DNR to evaluate how those resources will be used. This just talks about a little bit about those priorities. We've been doing remediation under the auspices of the Pollution Control Agency at most of our sites, but it's been pretty basic stuff. It's very much like the 1980s or early 90s in dealing with these, and so happily we're going to be hearing about some maybe better approaches to dealing with these chemicals in the environment, but because we started our work back in 2008, 2009 on the remediation, it was largely excavation, containment vaults, some incineration, and then groundwater pump and treat, primarily with carbon filtration. The good news is our own biomonitoring has shown as we remove exposures through treatment of the drinking water, concentrations in people's blood serum has dropped off at predictable rates based on the half-lives for PFOS, PFOA, and PFHXS. So we know that if we remove drinking water as an exposure route, it goes a long way to reducing levels of these chemicals in people's bodies. We've done a study that was recently published in Chemosphere on garden produce and did see some uptake of PFAS, and that's a minor exposure route, but it's primarily PFBA, which is the most water soluble, which is what you'd expect plants to be taking up. So did not appear to be a major contributor to people's exposures in those areas. I know I'm running a bit behind on my time, so I'm just gonna skip through this very quickly. We do have other sites. We've been not hit as hard by the AFFF issue as some other states, but we do have two major sites in the state that we are following. And again, at least one of those, the Duluth Airport surface water transport, again, seems to be the major role, playing the major role in moving the contaminants away from the site due to runoff to some surface waters nearby. We also have had a number of chrome plating sites that we've identified by tracing contaminants, initially detecting PFOS in fish and then tracing them back to their sources, either through a wastewater treatment plant and to a chrome plater that was discharging to a sanitary sewer, or through a stormwater system that ultimately went back to a chrome plater that had high levels of airborne PFAS that was being PFOS that was being deposited on their roof and then running off into the stormwater and infiltrating. So recognizing that there are lots of sources that are yet to be identified in the state, we are currently doing a pilot project, the Pollution Control Agency is, to try and identify potential sources. So they're doing a pilot project looking at industrial classifications, weighting each one by potential human and ecological receptors, and then we'll be trying to ground proof that methodology coming in the next couple of years. It was mentioned that ITRC has been doing a lot of work on this, so I've thrown into the slides some links to the information that ITRC has been developing on PFAS, and I would just encourage you to take a look at that. If you're able to come to a training, they provide a lot of good detailed information about PFAS and various aspects of it. And with that, I'm going to hand it over to Kristen to talk to you about the REGENESIS and their products.
All right, well, thank you, Jenny, for the very informative, I think, examples of how complex this problem really is. And so I'd like to transition and talk to you about a couple of case studies where we are using an approach of using colloidal activated carbon for an in-situ remediation approach to address PFAS. I'll quickly just go over a few of the PFAS challenges that I think Jenny has actually already highlighted quite nicely, and then talk about the approach that we're using of in-situ sequestration to address PFAS. And then finally, we'll get to 3 case studies where we've actually implemented this in the field and have data to look at. So again, I won't spend too much time because I think we saw this demonstrated very nicely in what Ginny talked about already, and that the challenges really are that we have large dilute plumes. I think these are textbook examples where we see them going across for miles. We're at low concentrations, and we're trying to get to even lower concentrations. We see states like Minnesota and others that are setting new regulations that are even lower than the health advisory level that the EPA has set in the last couple of years. And again, our issue here is that we have extremely recalcitrant compounds. So any approach that we've used for other types of contaminants just are not going to work for PFAS. We cannot destroy these readily in an in-situ approach. And so we've really had to revert back to pump and treat using either granular activated carbon or ion exchange. And if you think about all these problems and challenges together, it doesn't always make sense. Pump and treat isn't necessarily well aligned with large and dilute plumes. And so what's going to happen in these mile-long plumes is that we're going to end up having some areas where we have sensitive receptors at risk. So in this illustration, we see a plume that's approaching the surface body water. For example, going to a river, this could be a drinking water supply or, into a neighborhood. But all this together really highlights that there's a need for a flexible, low-cost in-situ strategy to address PFAS at this point. Such that the idea would be that we could actually cut off these plumes before they're getting to the sensitive receptors, and really removing that risk that the PFAS is including. Okay. So how could we go about doing this? Well, the strategy really comes down to the idea of eliminating risk. Again, we don't have a viable destructive option to date. And so then what we need to think about doing is something more like in-situ sequestration. So the idea of isolating and removing the contaminants out of solution. The goal here would be really to prevent the contaminants from migrating, which in the end removes our exposure pathway and removes the immediate risk. Another way of saying this is looking at the definition of environmental risk, which is the product of a hazard, in this case PFAS, times the exposure. If we can remove that exposure, we're going to thereby remove the environmental risk. And so that's really the approach here. And while we're talking about this with PFAS, this isn't a new idea. We are certainly accustomed to using this type of sequestration approach for other contaminants like metals, where we're trying to immobilize them, stabilize them to prevent them from moving, and again, prevent that exposure pathway. So how can we do this? Well, we know that granular activated carbon is used for ex-situ treatment systems right now. And so the approach that we've used and what we'll be talking about in the case studies that I'll be getting to shortly here is we've used our product called Plume Stop, which is a form of colloidal activated carbon. And so the idea here is that now where instead of using activated carbon in an ex-situ approach, this product actually allows us to use it in situ in a slightly different way. I won't spend too much time talking about the product, but the key thing to know is that this is a form of activated carbon that's formulated to widely distribute in situ under low pressures. And so the idea here is that we can actually inject the Plume Stop into the ground, let it distribute, create a passive barrier such that the barrier will then intercept the PFAS and prevent it from further migrating. And the key to all of this is the size of the activated carbon. It's very small, 1 to 2 microns, and that's what allows it to distribute, and especially to distribute under low pressure so that we get good coverage. Now, the mode of action with PFAS is that it's going to behave like any activated carbon in that it can absorb these compounds. I do want to point out that it's a dynamic adsorption, which really just means that it's not an absolutely permanent immobilization. Rather, the effect is that it significantly increases the retardation of the PFAS plume as it's moving. So to give you kind of a reference of this, a natural retardation factor created by the natural organic carbon that would be present in typical aquifers for PFAS, it might be on the order of 3 to 20. So that's how much slower the PFAS is moving relative to the groundwater. However, with being able to install a colloidal activated carbon, now those retardation factors will increase by many orders of magnitude. And in the end is what this relates to is that we can start to sequester these compounds for decades. And again, we're preventing the migration and removing the risk by doing this type of an approach. I'll just speak briefly to the idea of a colloidal activated carbon versus a granular activated carbon. And the take-home message really is that there is a benefit to taking an activated carbon and grinding it up into smaller particles. And this is based on some work that came out of Chris Higgins' group at the Colorado School of Mines, where basically we just see that the kinetics are much better when you grind up activated carbon to be a little bit smaller. This plot really is just showing this. The y-axis is showing the extent of adsorption versus time. And as what you can see is that if you take carbon, grind it up, you get much more adsorption in a very shorter period of time. And so there is a benefit to smaller particle sizes, to faster kinetics, which really just means that we're better utilizing the activated carbon when it's ground up. And one more additional point to the kinetics is also just, we're talking about using activated carbon in a completely different setting than what's typically used in an ex-situ pump and treat type system. So for GAC, you're talking about pumping conditions, which means you're going to have contact time on the order of minutes. So you have to have a lot of carbon to really get the same kind of an effect of removal. However, with the colloidal activated carbon, now we're injecting that into the groundwater. It's a passive system, and so we're working under natural groundwater flow, which means that the contact is not going to be weeks to months. So between this increased contact time and the faster kinetics really just means that we have better relative performance when you grind up activated carbon to a much smaller size. The last point I'll make just before we jump into the case studies is the approach that we take to really have a successful case studies when we're using colloidal activated carbon to address PFAS. The first one is that we really need to confirm distribution. We are trying to build an underground fence or an underground barrier, and so we have to know that we're getting good distribution. And so this picture here on the right is some examples of cores that were taken after the application of a colloidal activated carbon installation. As what you can see is we have good distribution. We know we're getting it where we're targeting it to get, which means we're building a good fence. And then the second is just the longevity of the performance. And so things that we take into account when we're making or creating a design is that we need to know any of the contaminants that are present, whether they're the target contaminants or any other species that can adsorb to the activated carbon, because they all will adsorb to activated carbon, and there can be some competition, which is something that we take into account. Next is the contaminant flux. So we need to know concentrations, velocity. Obviously, if something higher concentrations moving faster means that we're going to need to consider that to meet the targets of how long a barrier will last. And then the dose of the adsorbent is something that we can play with to try and increase that longevity. So now moving to the case studies. So to date, we've actually had 4 sites where colloidal activated carbon has been used to address PFAS. And then we also have an additional 9 that are in the queue right now. So I expect if you stay tuned, we'll have more data to be talking about in the coming years where we've applied this on additional sites. But for today, we'll talk about these 3 sites that have been performed in North America. And a couple of common themes with all of them is that these are all commingled plumes, either with TPH or chlorinated solvents, which I think is going to be fairly common with PFAS, is that we're often not going to see them completely on their own. And the range of contamination that we'll see at these 3 sites ranges from about 100 nanograms per liter up to about 5 parts per billion. So the first site was performed in Ontario, Canada, and I won't have time to go into much background on any of these sites, but I will point a nice resource for you if you're interested in much more background on this particular site. This was authored by Rick McGregor, who was actually the consultant on this site, and he does a nice job of explaining the application all the way to the results. If you're interested, this is available on our website. But what's interesting about this site is that the remediation was only being conducted because of hydrocarbons. The PFAS was actually not even known about when the original designs were being put together. However, just before the installation, Rick got wind of some history of the site and found out that there had a potential to be some PFAS on that site. And so in fact, he went and sampled just prior to the application, and he did find PFAS. So this is the extent of the entire site. And you can see down in this left corner, there are 6 wells that were impacted by PFAS and PFOA. And so the remedial approach, again, only based on the hydrocarbons, was that he was going to add in an oxygen release compound to aerobically degrade the compounds, and then add plume stop to prevent offsite migration. And so the fact that we had baseline data for PFAS meant that we could actually follow the PFAS concentrations at this site as well. So it was kind of a side story that resulted from the site. The monitoring events, again, PFAS and PFOA were the only 2 compounds that were looked at baseline, and then they were monitored quarterly for the first year, and then periodically for now almost up to 3 years. At the 1.5 year mark, the list was extended to include 12 additional analytes. So again, we don't know what those baseline concentrations were, but at least we're monitoring for them now to see if they would show up at any point going forward. And I'll show you the results from one of the 6 wells, which is, these data are really representative of all the wells. You can see the baseline concentration prior to the plume stop being applied, and within the first quarter, the concentrations had dropped to non-detect, and they've really sustained for almost 3 years. There's one hit of PFAS at one point, but that hasn't sustained. And then even when the additional PFAS compounds were added to the list at 1.5 years, those have also been non-detect going forward. So a nice example of where, we're observing the PFAS removed from solution, and again, removing the risk of any kind of plume migration. One additional side story I'll just point out briefly is that there has been some additional independent research associated with the site. So Grant Carey from Pore Water Solutions has initiated a study with Rick McGregor, as well as with researchers at University of Toronto and the University of Waterloo. And they've done a lot of modeling to investigate what the potential longevity of this actual application at this site has been. So their analysis included running numerical models, running some isotherms, and just looking at a sensitivity analysis to kind of think about the different circumstances of what might impact the longevity. And the key result here is really that they estimate decades of treatment from the actual application, the actual doses that were used at this site, and also taking into consideration that those hydrocarbons are present. So if you're interested in reading more about this, this article just came out in the last couple of months, but it's a really nice study that looks into the idea of the longevity of this type of a treatment. The second case study is at a US EPA Superfund site. This one is a little bit different. It was a solvent distillation facility, so numerous VOCs had been released over the years, and also numerous remediation strategies have been implemented to address those VOCs, one of which included installing a hydraulic containment system with the sheet pile wall and some pump and treat systems. As of last year, the pump and treat systems, which were located just inside of the wall, were turned off, and to prevent any kind of mounding, there were perforations actually cut into that sheet pile wall to allow the groundwater to flow back through. There is some residual groundwater contamination coming from the source area that includes some low-level VOCs, and then also recently found PFAS. And so the target here is really to address the contaminants that are flowing through those perforations in the sheet pile wall. And so plume stop was used to address the PFAS migration, and the target at this particular site is to have a total PFAS concentration of 70 parts per trillion or less of the sum of these 5 compounds that you can see listed here. So the plume stop was installed just inside of the sheet pile wall and is being allowed to kind of flow through those perforations. And again, the results here we have almost 3 to 4 months of data here, is that the data I show here is from 3 different locations, one of which is within the application zone, right where plume stop was applied, and you can see a very immediate decrease that has sustained over time. Again, that's where you're going to see the most impact, right where the plume stop was installed. However, we're also seeing decreasing concentrations in the down gradient wells. As that PFAS is intercepted, as you'd expect, the concentrations will be decreasing as you move down gradient, so even 10 and 50 feet down gradient in those wells. And there's a second application that's planned to be installed shortly, and that's really just going in with some new dosing that's optimized now that we have a little bit better understanding of the flow dynamics that are going through those different perforations. But another good example where we're seeing the effect of removing the PFAS from solution. And the final site is from Grayling Army Airfield in Grayling, Michigan. So this is a National Guard training center that over the course of the operations that happens there has had numerous contaminant releases, including diesel, chlorinated solvents, and also PFAS. And so PFAS is a current driver, considering especially offsite migration into local communities. And so we worked with the Michigan Army National Guard to conduct a pilot test in this former bulk storage tanks location, where there's some residual PCE as well as about 130 total, or 130 nanograms per liter of total PFAS, which is primarily PFOS and PFHXS. And the strategy here was to create a simple cutoff barrier. So plume stop was installed, you can see on this illustration, in this type of a barrier, with the idea of just preventing migration of that PFAS any further offsite. And we'll look at the data from both. There's a couple sets of wells here. There's an upgrading well set and there's a couple downgrading well sets. And so that's the data that we'll look at from this site. So we're looking at about 6 months of data here. These are the upgradient wells. And so you can see the relatively constant concentrations of the flux that's coming into that barrier. And then these downgradient well sets, again, we're seeing something similar that we've seen at these other sites, where within about the first month or two of sampling after the installation, the groundwater concentrations of PFAS have dropped to non-detect and have really sustained throughout those 6 months. And these particular wells are 6 and 16 feet down gradient of the barrier. However, just recently, we've actually installed a few more sets of wells that go down even to about 45 feet down gradient of the barrier, and we're seeing good results at those wells as well. So this is a quick overview of a couple sites where we've done this, but the summary really is, at the beginning, I described that there's a need for a flexible, low-cost, in-situ option to address PFAS. And we really, I think, are in need of this in our toolbox to pair it with pump and treat, considering the limited options that we do have. And what we're seeing is that Plume Stop is able to provide that tool within our toolbox. The method in which it operates is that we're talking about eliminating the risk of PFAS by removing the compounds from the dissolve phase, preventing their migration, and removing that exposure pathway. So the data from these sites have been quite promising. We're excited to continue monitoring and also to see this apply to additional sites where we'll have a little bit more data to be presenting here in the future. So with that, thank you all for attending, and I think we may have a few minutes for questions for either myself or for Ginny.
All right, thank you, Kristen. That does conclude the formal section of our presentation. So as Kristen said, at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of quick reminders. First, you'll receive a follow-up email with a brief survey. We really appreciate your feedback, so please do take a moment to let us know how we did. Also, right after the webinar, you will receive a link to the recording as soon as it is available. All right, so let's go ahead and circle back to the questions. We have several questions here. This first one here is for Kristen. And the question is, what is the long-term outlook for colloidal activated carbon? Is there some long-term plan to remove the colloidal activated carbon and PFOS or the sequestered sediments?
Yeah, so on a typical site, I mean, the answer would be no. I mean, the plume stop becomes part of the soil matrix, and it will absorb these compounds. And, as we saw in the longevity study, that we expect this can last for, for decades. The idea, though, is that, I guess the optimistic outlook here is that over the next couple of years, we'll have some sort of destructive technology that can be invented, and perhaps we can go back in and then start to destroy these. But there's certainly a possibility if the site was right to go in and excavate, but that is not the typical approach.
Okay, all right, so next question, this also for you, Kristen, and it is, can the carbon injection be done at point of use? In other words, at a drinking water well to directly protect the receptor?
Yeah, so that is one scenario that we have certainly thought about doing, and I think have had some conversations, is that you could imagine surrounding a well, or perhaps the area where you're pumping from, and as a way to pre-treat the water that is being pumped out of that well. So that is certainly a viable option to be considered, and hopefully we'll have some examples of that in the future.
Okay, thanks, Kristen. Let's see, we have a lot of questions here. Several questions for you, Ginny. Multiple people are asking some variation of this question, which is, do you know like exactly what the source of the PFOS was at the chrome plating facilities, and where would we expect to find these constituents in the groundwater column?
Yeah, so the PFOS was used, it was a product used as a coating or a film on the chrome vats, and it was actually a personal protective application to prevent to reduce the surface tension on the vat, so that when there was bubbling, it didn't create fumes that were coming off of the vats or mists coming off the vats that the workers would inhale, because chrome 6 is a highly toxic chemical. And so it's still actually an exempt use under the phase out of PFOS. It's just most platers have moved away from using PFOS based products. Although I know the Pollution Control Agency at one of those sites found that even some of the replacement products were still contained PFOS, and so it's an interesting question about where the PFAS chemicals are going to be found in the groundwater column. Because they're surfactants, they will have a tendency to partition along the air-water interface. But our investigations out in the Washington County area at the disposal sites show that they basically go where the water goes. And so although there may be some partitioning at those interfaces, we're finding them, migrating downward with the groundwater to depths of 300 or close to 400 feet in some instances. So I think you have to look everywhere, but we did do a little bit of sampling when we were doing our surface water sampling, and we did see that it wasn't exhaustive, and it's almost more anecdotal in terms of the data set that we have, but we did see slightly higher concentrations at the air-water interface than halfway down the water column in the surface waters that we were testing.
Okay, thank you, Ginny. Yes, lots more questions here. Another one for you, Ginny, is has PFAS been detected or found in the Mount Simon aquifer in this extended area in South Washington County?
I don't believe we've found it any. There are a couple multi-aquifer wells out there that even go all the way to the Mount Simon, and so I can't say for a fact that there was nothing, but as in my recollection, we have not seen PFAS in the Mount Simon yet.
All right. Let's see here. So here's another question for you, Ginny, is has there been any population studies done in the St. Paul area looking for correlations between elevated levels of certain disorders or diseases and well concentrations, similar to what was done in Ohio, west of the Parkersburg, West Virginia, Washington Works plant?
Yeah, so we've not done a study like the Ohio, West Virginia study, which was an actual direct health study that was funded out of the litigation against DuPont. We're actually in the process of looking at the Agency for Toxic Substances and Disease Registry right now is looking for proposals for similar types of studies to be done across the country. And so we are evaluating whether we can do that. But what we did look at was reported rates of illnesses in those communities. Now, I want to preface this with, I'm a hydrogeologist, I'm not a toxicologist, I'm not an epidemiologist. So there is information on our website about those assessments, but we did not see elevated rates of the cancers that have been associated with these chemicals. That's actually not surprising, because typically the
primary concern is more subtle effects, non-cancer effects for developing fetuses and infants. And so the other things that have been attributed to PFAS exposures, such as increased rates of miscarriages or lower birth weights, again, the available data that we have suggests that we don't see any increase in incidence of those, but again, it's best if people have specific questions about that to visit our website and look at the information that's posted there.
Okay, thanks, Ginny. Maybe time for one more question. This question is for Kristen, and it is, how do you keep the efficacy of this colloidal activated carbon treatment over a 10 to 60 year period?
I think the good part is that the idea here is really to have a single installation. And so part of this comes from the upfront work of the design and an understanding of what the goals are and what the contamination levels, the flux, any other competing species might be. But the idea is to create a design that you would implement one time, and then that would last for that particular length of time. I think the other good side of this is that we would certainly recommend continuing to monitoring to monitor at downgradient wells, and if there was some sort of breakthrough that came through, we'd recommend that you can go back and you can reinstall another dose of plume stop at an additional date if there's some new contamination coming through, and then that would add on another layer of protection that would extend the lifetime of that barrier. So again, the idea is to have a single installation, and then it will do the work for that amount of time.
Okay. All right. Well, thank you very much, Kristen. Thank you, Ginny. That is going to be the end of our chat questions. We are out of time. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about remediation solutions from REGENESIS, please visit regenesis.com. Thanks again to Ginny Yingling and to Dr. Kristen Thoreson, and thanks to everyone who could join us. Have a great day.